Hello everyone, we are Group 4 and we are going to present Activity 4 entitled Solubility Diagram, Partially Miscible System. Miscibility is the property of two substances, which are often liquids, to form a homogeneous solution. When two liquids are miscible, they will mix completely in all proportions, and we will observe a single phase in the resulting mixture. Following the rule of thumb, like dissolves like, liquids are miscible when they have very similar polarity, such as water and ethanol, and benzene and cyclohexane. Meanwhile, if two liquids are immiscible, they will not mix and we will observe two layers that are separated by a curved meniscus. For example, when we mix water and oil, or water and benzene, which have very different polarities. But liquids can also be partially miscible with each other, meaning they are only miscible to a limited extent. Examples would be mixing water and aniline, water and bromine, and water and phenol. When we mix a small quantity of one liquid to the other, we observe complete miscibility, but when we add larger quantities, layers would form such as in the left figure. The lower layer consists of a small amount of water dissolved in bromine, while the upper layer consists of a small amount of bromine dissolved in water. Also, the solubility between partially miscible liquids is dependent on the temperature and pressure, though changes in pressure have negligible effect for liquids compared to gases. The solubility of two partially miscible liquids may increase with increasing temperature, which we call the maximum solution temperature type, or the solubility may decrease with increasing temperature, which we call the minimum solution temperature type, or there may be an intermediate temperature region such that the solubility may decrease then increase with decreasing temperature, which we call the maximum and minimum solution temperature type. The variation of solubility with temperature can be illustrated with what we call a solubility diagram. For partially miscible liquids, we commonly use a temperature composition diagram. With this, we can visualize the phases present in the system under specific conditions of temperature and composition, and we can determine when the system will be single phase or homogeneous, and double phase or heterogeneous. For the maximum solution temperature type, such as in water and aniline, there is a temperature at which we first observe complete miscibility, which we call the critical solution temperature or the consolute temperature. To be more specific, in this type, it is the upper critical solution temperature or TUC. Below this temperature or inside this curve, there would be two layers present where each liquid would be a minor component of the other, while above this temperature, the two components are fully miscible with each other and we would have a single phase. The solubility increases with the temperature due to increased kinetic energy, which breaks apart the bonds between the same molecules. On the other hand, for the minimum solution temperature type, which is in the case for water and triethylamine, we would have instead a lower critical solution temperature. This is usually in the case for components that form weak complexes at low temperatures. When the temperature is high, the complexes break up and the two components are less miscible, so we would have a two-phase system. There are also cases when we have both upper and lower critical solution temperatures, such as in water mixed with nicotine. This occurs when, after the weak complexes break up, the thermal motion at higher temperatures homogenizes the mixture again into a single phase. Solubility diagrams have many real-life applications, such as in industries for the purification of a certain substance from binary liquid mixtures. They're also important for pharmaceuticals to determine if administered drugs can be absorbed by the body through the fluids such as stomach acid or blood. And lastly, they're also important in showing the conditions at which different metals can precipitate out of water in order for the metals to be filtered out. So in our experiment, the main objective was to determine the solubility of the partially miscible pair phenol water. Specifically, we would construct their mutual solubility curve from given data, and then estimate the critical solution temperature of the phenyl water system.
Now for the methods, we start by preparing the phenol solution. So in a pre-weighed graduated cylinder, we add the 20 ml melted phenol. Then we weigh this to obtain the weight of the phenol. And then after that, we add the distilled water, which is 1/4 the weight of the phenol, and we stir it thoroughly to mix. And then after that, we transfer the solution to a burette. Now for the next part, we dispense 10 ml phenol solution to a 50 ml test tube. Then this was fitted with a cork, thermometer, a copper wire, which serves as a stirrer. And then we add distilled water until the solution became cloudy, and this was stirred occasionally. After it became cloudy, we record the volume of distilled water added, and then we heated it in a water bath while stirring occasionally until it clears up. When it clears up, we record the temperature, and that is the clearing temperature. After that, we remove it from the water bath, and then we also take note of the temperature of when it becomes cloudy again. That is the clouding temperature. Then we add another 1 ml of distilled water and then repeat the procedure. That is repeated 5 times. Here, this is another part where phenol was the one added to water. So 10 ml of distilled water was dispensed to a 50 ml test tube, fitted with a cork, thermometer, and copper wire. And then we now add the phenol solution until the solution becomes cloudy. And we record this, the volume of the phenol solution added. And then we heat it in a water bath while stirring until it clears up. We record the clearing temperature again, and then we remove it from the water bath. And as it cools, we notice that it becomes cloudy again. Take note of the temperature. And then we add another 1 ml of phenol solution, and that is repeated 6 times. Here is the data analysis. We calculate the average of the clearing and clouding temperature for each run, and then from there from the volumes of the phenol and water, we calculate the percent weight phenol, and then we plot this average temperature versus percent weight phenol, and that will result to a solubility diagram of the phenol water system. So here are the results that we obtained. These are the clearing temperatures for runs 1 to 6. By the way, this is from adding water to phenol. And okay, this is the clouding temperature. And then of course the volume of the phenol solution is constant, 10 ml. And then the volume of water increases per run. So in here, the average temperature is the average of the clearing and clouding temperatures per run. And we obtain the rate of the 80% phenol solution by multiplying the volume of the phenol solution times the density of this 1.05 grams per ml. And then rate of water is the volume of water added times the density of water. And this is obtained, the percent weight phenol, by this calculation. This is the weight of the phenol solution multiplied by 0.8 since it is only 80% phenol. And then this is divided by the total weight of the solution, which is the weight of water plus the weight of phenol solution, and then multiplied by 100, we obtain 53.92%. That's for run 1. Next, this is the data obtained from adding phenol to water. So we see here that these are the clearing temperatures, the clouding temperatures, And then the volume of water is constant, while the volume of phenol solution increases per run since we add more and more of the phenol solution. So here, similar to before, we take the average of the clearing and clouding temperatures. These are the results per run. And then we obtain the weight of water by multiplying the volume water times the density of water. And then we obtain the weight of phenol by multiplying the volume of phenol solution times this, 1.05 grams per ml. And then we obtain the percent weight phenol, which is this, the weight of phenol solution multiplied by 0.8, which is again 80% phenol, then the total weight of the solution, and we obtain the 8.31% per run 1. Now this shows the summary of the percent weight of phenol calculated from the previous tables, and then their corresponding average temperatures. So from what we can see here, the blue points are those when phenol was added to water. So mas malaki yung percentage ng water. And here is when water was added to phenol. So higher percentage weight phenol. So yeah, when this is plotted, this as the x-axis and then this as the y-axis, we get this solubility diagram of the phenol water system. And then one thing to take note from here is the critical solution temperature, or the upper consolute temperature. Specifically upper kasi this solubility diagram is a maximum solution temperature type kasi may maximum siya. And this was determined to be 66.11 degrees Celsius. This was how we determined the consolute temperature or the critical solution temperature using differentiation. So, sa Excel, nag-generate kami ng best fit line, tas ito yung lumabas na equation. Tapos, dinifferentiate namin yung equation na yun. We obtained this, and then we equate it to 0 to obtain the critical numbers. And the critical number value of x that we obtained was ito, 0.26670. And then, ito yung sinubstitute namin sa original function. And then, the y value that we obtained was 66.11. And that corresponded to the y-axis, which is the temperature of the solution. 66.8 yung literature value ng phenol water system. And comparing this with 66.11, medyo close na yung values nila. Kaya 1.03% lang yung percent error.
So this experiment used the clearing and clouding temperatures to estimate the upper consolute temperature. Since phenol has a melting point of 42.8 degrees Celsius, it is expectedly solid at room temperature, which means that the solution also tends to solidify at high concentrations of phenol, thus causing the solution to become more turbid as it becomes more saturated with phenol. So because of this, turbidity is used as a measure to determine the presence of two phases. And as the temperature increases, the solution visibly turns clearer, which means that visual solubility also increases. So the increase in solubility with temperature indicates that our phenol water system is a maximum solution temperature type. For a system containing two partially miscible liquids, such as our phenol water system, the composition of the layers should remain the same at constant temperature. So for our system, this means that an addition of phenol or an addition of water would only change the relative volumes of the two layers, but not the composition of either the water-rich or phenol-rich layer. So to further understand this, we turn our attention back to our solubility curve. So suppose we have a phenol water system of composition A, The composition of the two layers in the mixture are given by B and C. If we add more phenol to the vessel while gently stirring and maintaining a constant temperature, the system point moves to the right along the tie line. Say we arrive at point A prime. If we apply the lever rule to the ratio of lines from A prime C and BA prime and compare this to the ratio of AC and BA, we see that the relative volumes of the two layers actually changed. We also see that the volume of the phenol-rich layer increases at the expense of the water-rich layer. However, since we're still at the same tie line as point A, and because the ends of this tie line are fixed, the two layers actually do not change in composition, and only the volumes of each layer is affected. So similarly, if we keep the overall composition constant at point A, but we raise the temperature, the system point actually moves upward, and the compositions of the two layers will change since we are now in a different tie line. So the relative volumes of the two layers also change until we reach the temperature corresponding to point D, where we would be left with only one liquid phase. So as we continue to increase the temperature, we reach the consolute temperature at the peak, wherein the composition of the two layers become identical, thereby exhibiting complete miscibility. So above the consolute temperature, the two liquids dissolve in each other in all proportions, and this is why the area above the curve indicates a one-phase region, while the area inside the curve indicates a two-phase system. As for sources of error, one of the primary sources of error in this experiment is relying merely on visual inspection to estimate the upper consolute temperature rather than differentiating the curve. So, the value of TUC that we would get from visual inspection is actually close to theoretical, but differentiation of the solubility curve will give a more accurate estimation of the TUC. Parallax error, of course, is also a contributing factor to errors because parallax error is easily committed when measuring temperature and liquid volumes in glasswares. So another source of error would be the presence of impurities in the setup, which could act as an additive to produce an otherwise ternary system. The impurity may lower the critical temperature if it is equally soluble in both components, while it could raise the upper consolute temperature if it is readily soluble in only one component. Last would be the production of pressure in sealed tubes, which may cause a slight increase in the critical temperature value. So, in summary, miscibility is the property of two substances to form a homogeneous solution. Phenol and water are partially miscible because an addition of phenol or water only changes the relative volumes of the two layers but not the composition of either layer. It is also a maximum temperature solution type because solubility increases with temperature. A mutual solubility curve for the system was constructed, and the upper consolute temperature was calculated via differentiation and was determined to be 66.11 degrees Celsius, which is fairly consistent with theoretical. So, above this temperature, the two components become completely miscible in each other, forming only one homogeneous phase, and it was thus established that the miscibility of the two liquids is a function of composition and temperature. So for future experiments, we recommend the investigation of other types of partially miscible liquid systems, such as triethylamine in water, which is a minimum solution temperature type, and nicotine in water, which is a maximum and minimum solution temperature type. Salts can also be added to the system for clear visualization of layers or phases. And in the case of phenol water system, the effects of salts in reducing the miscibility of phenol and water and why this results in an increased critical temperature can also be explored. So here are our references, and thank you for listening. So if you have any questions, feel free to ask us at our Canvas discussion page. We will also be happy to know your feedbacks for this video. So thank you.